Welcome back to another C programming speedrun challenge. This is already late, fortunately, but it's a little bit of linked list action we got today, so let's hop right in. Arrays, pointers. Okay, yeah, this looks pretty normal. No global variables. Yeah, that should be fine. Because we just have our head pointer as like a local variable. And then it looks like this is going to be our node type this is going to be the data we actually store in each node. I hate the upper caps. This is not going to be good. Oh, this doesn't look too bad. Okay, so yeah, point to the head of the list. Okay, we got to do some I/O. We'll probably have to save this after when we're done too. Okay, yeah, so basically just printing it, searching for a specific thing. Adding to the end, deleting. So it looks like we're gonna have to search for, it looks like the job number is like the way we query everything. So that shouldn't be too bad. We just gotta do some linking stuff. Yeah, and then this is like, what is this, average job size? Okay, yeah. Yeah, so then basically this is like traversal, and then this is like actually manipulation. And then I wonder if on quit he wants us to save or like, oh yeah, so once it's selected, write the contents to the same file. Okay, that makes sense. Test it, yeah. Shouldn't do anything. Okay, so yeah, it sounds like he wants us to do a different function for each one of these cases. That's probably the way I do it anyway. It just makes it a little cleaner. Okay, let's see. Yeah, all right, let's get started. So I just have like an empty terminal thing here. We'll just paste this in. What's today? 2/18/24. And it's going to be like struct. Actually, let's move this to this page so we can reference it. We're probably not going to need to compile this for a while, so I'm just going to get rid of this. This is going to be, I hate this naming, dude. Data type, like what is that? This should be like job data or something. Semicolon, and we might have to do like type def struct. I don't know which. I'm not super specific on like what's a C++ feature and what isn't, so we'll make it work. Okay, we can rename it later. No globals. So yeah, that's going to be our data. We also need like let's call it node type. Shoot. Ooh, my Vim. Okay, and so basically this is going to contain our actual data. Oh no, this isn't Rust. Data type, data, and then we'll just do like next node type pointer. Right, so this is going to be our linked list, so this is null at the end. And these have to be struct. Yep. Main. Hopefully we can get this to pull up here. I always forget. I forgot like the order of the args. Okay. Yeah, we use the double pointer because it looks cooler. Whoops. Okay, so we need this. Paste, and then that's our main. Oops, what am I doing? Okay. Yeah, so inside main, it looks like we're basically going to read in. Wait, is there any arguments here? Oh no, I guess we just read this hard-coded file. So let's do like data file, right, just so we can have this as a constant, because we're going to have to use this in two places for reading and writing. And then I guess we don't need arguments because we basically prompt the user in like a list for whatever they want to do with the program. And then we're just going to have like while true. What can we even do? Oh, we have to do while one, no. Or we could do like the for semicolon, but I like while better. We'll just assign it to 0 so we don't get DOSed, right? And we're gonna have to call scanf to basically read this in. This is gonna be probably %d. I guess the linter will yell at us. Yeah, okay, we'll include stdio, and it has to be a pointer, right? Because yeah, it's gonna write to it. So then we're going to say if, let's see, So if it's less than 0, I think 0 is a thing, right? Oh no, there is no 0. So if it's less than 1 actually, or it's greater than 6, then we're basically going to say invalid input, right? And we'll exit the program with 1. Import this. So we're going to say like choice and we'll do a little bit of Rust syntax here just to be sneaky. Yes, we exit, so now we know it's in range, right? And now we can do, he probably is prescribing some weird, yeah, he wants us to do this in a specific function. Honestly, I would just have the switch here, because I think this other function is kind of unnecessary, but he's the boss, so yeah, that's what we got to do. Actually, I'm going to call this choice instead of input. It's just a little more clear. Okay, so we validated that. Actually, we'll just do... Because the problem is I don't like having these weird preconditions, right? Like, the problem is breaking this up into a separate function means that we have to be like... must be 0 to 6, right? But if we just put the validation here, then that's fine, right? Because then we can fail in this function, and then all main has to worry about is reading the input. But it sounds like he doesn't want that. He says process choice is basically just supposed to be a naked switch, and then it dispatches to whatever other function. So I don't really like that, but again, he's the boss, so whatever. And then we're also going to have to do something like outside the loop, like this is going to be node type. So basically this is going to be our head. Load data, and we'll make this like a nice function. And I think he wants to remain at the top actually, so we have to do like sorry, node type pointer equals path, right? We're going to do fopen. This doesn't have to be a file name, it could be a full path if we want. And this is the return type, yep. And then we're also going to be, let's just create this right away. We're going to say save data, right? And this is going to be kind of the opposite, where it's going to return void, right? Because it only writes to the disk. This is the path we want to save it to, and then this is the head of the list. And then let's put these declarations up here so this can compile without the implementation. And we need struct everywhere because C is very verbose. Okay. So yeah, we call load data. Here we'll call process choice. I think that's how you write a switch. Oh no, we need parentheses. Case 0. And so because we're storing the head inside main, right, we can't have any global variables. So actually some of these choices, like imagine, so let's say we start out, we have an empty list. Someone says add job. Now this head pointer goes from being a null pointer to being a pointer to the very first thing in the list, the only element. And so actually in process choice, that's where it gets created. And so we're actually going to have to, because we're modifying the list, we're going to have to return the new head pointer, right? Because imagine like its first iteration, we're basically creating the list, or if we're adding a job, oh, I guess it's always at the end, so never mind. But yeah, we do need to modify this if it's the first time. And we're just going to have default as well. This is also another like invalid precondition. Actually, we shouldn't fail this here. We'll just say, actually we can just do else here, right? And then the next iteration of the loop will handle it. And we need to declare process choice as well. Okay. And this, so basically, so we have this comment here saying that the precondition, it must be 0 to 6. So if this is running, we do want an error, right? Because that's a programming error where someone isn't abiding by our contract. So we're going to say process choice failed. Oh man, I really can't type today. Failed precondition with lower p. And so case, we're going to do like return. Oh no, there's no 0. And this, we need to correct this as well. Actually, Oh, we also need to pass in the head here. Node type pointer head. Actually, yeah, because I'm starting to not like this default business. Because if we get an invalid choice, we can just simply do nothing. That's probably the most sane thing to do here. And so in case 1, that's going to be display all jobs. So we need to call that function because he wants us to do a function for each thing. Display jobs, this only takes the head, and it's basically going to be this 1, 2, 3, 4, 5, 6. In case 6, this is going to be, we're just going to call save data to data file and head, and then exit the program, right? So because we don't want to be in this loop anymore. And we'll just fill in all these cases. Whoops, we need another one. Here's 5, and then we'll just rename all these functions to search jobs, add job. And I guess an add job we'll do more scanf stuff to read in the data. Delete job. Okay, and then we're gonna have to stub out all these functions. And these are going to be kind of similar to what we have before, where process choice. Okay, yeah, process choice definitely has to take in this also, right? That matches now. And here we're going to do the first one, which is display jobs, right? And then we're going to have one of these for each thing, right? We're just doing our declaration here. Hopefully our LSP will help us here. Add job. Delete job, get average job size, and then, yeah, actually we'll call save data here, so we don't need to do anything. And actually these, whoops, I didn't mean to copy paste like this. These only take the head pointer, right? Because this function is only implementing a single choice, right? We do have the switch in process choice, so it literally, this is just doing a single operation on the list, which simplifies things a little bit. And this needs struct. Struct as well, and we'll just basically stub these out in case we accidentally call it. I wish we like a to-do macro like Rust, then at least we'll know that. Right, so if we call this function by accident before implementing it, we'll see this exit code in fish, and then we'll know like, hey, we messed up, and we still need to implement it. So choice and then head, and we're going to reassign to head, right? Because imagine we create the list and process choice in add job for the first time. That's going to return us a new head pointer that's no longer null, right? Because this might be null if there's no data initially, and we want to reassign that so that next time in the loop we can search or add more, delete, whatever, right? Okay, so this is looking pretty good so far. I'm just going to copy all of these again so we can implement them down here. I'll basically just stub this, and then I'm thinking the first thing is probably the IO, because that's the easiest to test. It's probably just like fread and some memcopy stuff. Okay. All right, so load data. We get our path, and so we're going to do file we'll probably have to implement or import the null thing, and this is going to be read binary, right, because we're not modifying it. Printf, and here we want to just say, hey, open the path with a new line, right, so it wraps nicely, exit the program. And now we want to basically read the data. So how do we get the size here? It'd be nice to, if we can just assume that the size is small and only have a fixed size buffer. Actually, we can just use, I don't know if there's a direct function here. We can do fseek, that's fine. Yep, okay, copying code from Stack Overflow, my favorite. So once we have the file, fp, bro, this is file. And then we're gonna have to reset to seek. How do you do start? Oh, seek set to set back to 0. I think size t is the type. these? Do we have these imported? Yeah. So stio, stlib. We're probably going to need string.h for like memcopy and stuff later. Okay. So yeah, we get the size, and now we're going to say void pointer buff equals malloc size. Yeah, I hate these. Like, dude, we're not in 1970 anymore. We have enough characters to spell out size. Buff, just do some error handling here. Equals null. Then we couldn't allocate memory, right? So we want to handle that. Oh. This should really never happen, dude. Like, I have. Yeah, I've got 64 gigs of memory. So if we're running out in our dumb C program, then we got big problems. So buff. Okay. So yeah, we made our buff. We know it's valid. Now we can just read the whole thing in. And what's this? Shoot, I forgot. So it looks like it takes dest size, the number of like records basically, which is gonna be 1 because we're reading in like one massive block of bytes, and then file. So this can be buff size 1 and file. And this is going to return the number of bytes read, right? So this returns unsigned long bytes read equals, and then, so the problem is this might actually not read the whole thing in one go. If, let's say, the file gets truncated between when we look for the size and actually try to read it, and so we want to handle that, because otherwise we're going to have missing data and we're just going to read in some garbage. So if the number of bytes we've read isn't what we expected, so if it doesn't equal size, then we want to say, I mean, ideally we'd want to put this in a loop, right? Because the kernel might decide to only do less reads. And fread, it has its own buffering scheme, I think, around the actual syscalls. But if we ask for this many bytes and the file has it, it should give it to us, even if we're not doing a proper loop. So this is fine to fail here. So we'll just say file size changed while reading. Right, so we're just printing out the size so the user can see what exactly went wrong. So we expected to read size, but we actually were only able to read bytes read. And this is crying about the format. That's fine. We'll just change this. Oh, ZU and LU. That's funny, yeah. So we call fread. So now we know we read the entire thing. So that's good. We have everything in memory. Now we need to figure out the number of nodes, actually. Because basically what I'm thinking is that we can't write a linked list out to a file, right? Because this pointer only exists within our program. And so when we save it to a file and load it later, none of these pointers are valid due to like virtual memory and address layout randomization. So what I'm thinking is basically for each thing in the list, we just concatenate these 3 ints together and have them like in a row after each other. But then the problem is this is what, 12 bytes, because it's 3 ints times 4 bytes. And so actually if we get in a file that's 24 bytes, then it means we have 2 of these instances, right? Because there's the first 12 bytes are the first one, and then the second 12 bytes are the next one. And so now we need to say like size divided by size of, what is this? Data. I really hate that name, dude. It's totally messing me up. No, I don't mean Sterling. What? Oh, actually, that's a good job. Good job, Clang. Data type. And this has to be struct. Yeah, okay, that was actually good. Yeah, because that just would have been the size of a pointer, which would totally mess us up. Okay, so now we have the number of elements, and we can start our for loop here. Actually, we're going to need to have our head. So node type pointer head equals null, right? Because an empty linked list is just a null pointer because there's nothing there. And we're going to do for int I equals 0, I is less than elements I plus plus, right? Oh man, Vim really doesn't like this formatting. Like, look at this. So when I hit enter, it puts the tab here, which is 4 spaces, but the LSP only likes 2. So there's a little battle going on here, whatever. And so we want to read this next chunk of data, right? So we're going to say we're going to have to cast this, right? So basically we have our buffer, which is just, or it's not even bytes, it's just any void thing, right? It's just a bunch of memory, and we want to read this data out of it. And so here's what we can do. We can say source data type pointer source equals, and we're going to have to basically cast buff at a certain index, right? So basically I times size of data type will give us the byte offset. Struct. Right, so basically at I times whatever, so when I is 0, that's going to put us at byte index 0, which is the start of this first object. Then if you imagine in memory, we have the second one right after. This I times 12, or whatever the size is in this case. Value equals 1, that doesn't look right. Whatever, it's probably some LSP thing, right? That'll bring us 12 bytes into the data, which will start us here, and then we cast the pointer to a data type so we can actually read it. So this should work. We're going to want to create our dest. And it can be uninitialized because we're just going to memcopy it. And we're just going to memcopy the address of dest, source. And this can be a const pointer. We're not going to read from it. Struct data type is the number of bytes. I think memcopy technically takes void pointers, but that's fine. Yeah, okay, so now we have the data read in a dest. Now we need to actually create the list. So we're going to do like struct node type, I don't know what to call it, new. This is basically the next node we're creating on the list. Let's just call it new for now. I know that's a keyword in Java, so it's bad practice, but who cares? Node type, and we're going to have to allocate this on the heap, right? So node type is this type so that we can assign it into this pointer field. And so we're going to call malloc. This is all the same, except it's not going to be size of data type. It's going to be size of node type, because that's the thing we want to create. If we mixed up this size, our code would totally break. Struct node type, what are you crying about? We probably need to cast this. Yeah, because malloc. Oh, I didn't even call malloc. Yeah, well, we have to do this anyway, because malloc returns a void pointer, because it's just allocating kind of raw memory for you. And we need to spell struct correctly. Yep, spell struct correctly. So now we have this. This might be null if it couldn't allocate memory. So lots more fun C error handling. If this is null, we want to get out of here because we can't do anything. So unable to allocate memory for node and then exit. Otherwise we know it's valid, so we can start doing stuff with this. And actually we don't want to create this dest on the stack, sorry. We want to copy directly from our data buffer into this new list pointer. So actually our dest pointer is going to be the address of new.data, right? Except new is a pointer, so you have to use the pointer syntax. And so basically this is going to move right from this data, right, which comes, or this source, which comes from our buff we read up here from the file. And then we're going to stick that directly into the data pointer of the node. So that means now we're half the battle's done, right? We initialize this, now we just have to set up the next stuff if there happens to be a next element. And so we also need, we need to store the head, first of all, so that we can return it at the bottom. But we also need to keep track of the last pointer we had, so we can link the two together. And so now that we've initialized this, so kind of the base case here is when I equals 0 on the first iteration, we want to assign to head and last so that we can start building the list. And then if last doesn't equal null, we want to link this new node to the last one. So do the first thing first. So if head is null, then head equals new, last. Actually, we want to do last equals new every time, right? So we kind of go to the next one. And so if last isn't null, that means there's an element before us that we want to attach ourselves to. So we do last next equals new, and then we want to keep shuffling this around, right? So then on the second iteration, last will be the first one, and then we create the second one. This won't run, right? Because we already assigned a head, so we can return that original pointer. But then this will run because the last one is set to the first one, new is set to the second one, and then here we're linking the first one to the second one, and then you can chain this, n times for however many elements you have. So yeah, I think this code should work actually. The next thing let's do is we'll implement display jobs. So we can actually use this to test our reading code, right? Because basically this is just pointing out the list we create, and here we create the list. So these kind of go hand in hand. So display jobs, we're basically going to say while head isn't null with the caps. I love that this is just defined as 0. Like, gotta love C. So while it's not null, let's see, I want to try and make this a little bit fancy if we can. So we're going to have like a new line at the end. And we're going to say, and yeah, so basically this order matters, and we're searching by job number. And so actually, yeah, let's print out the order here. Actually, we can use ++. This is in Rust. So we're going to say job number %d, and we'll do I+1 just so that for the user it starts at 1, so it's a little more intuitive. And we'll do a colon here and a new line so it looks nice. And we can just literally copy this stuff. And let's see if I can do this with a Vim macros to make it nice and fast. So we're going to do, we'll just do %d, comma. Oh, that's not right. Head. There we go. And this is the node type. Whoops, we have to go into data actually. So this is going to be head. Head is a pointer. Right, and so actually we're using dot here because data is just a normal field, it's not a pointer, so we don't need to dereference it. That can be a little tricky sometimes. And then we'll do some spaces so we get nice formatting, and we'll say like job type. Right, so the field names, I don't like this either about the naming. This is obviously a job, right? This should really be like struct job data, right? Not in all caps and not with underscores. And then this would just be like, number, type, size, right? But apparently this guy's garbage at naming, so we got to roll with that. So yeah, we just print that up, and then the last thing is we need to move on to the next node, right? Otherwise this will loop forever because we never change head. Next. Okay, now this should work. And actually this doesn't modify the list, so we can actually return void here. We have to change the declaration here. And we actually do this for the other ones. Search job isn't going to modify it. Get average job isn't going to modify it. But delete and add may. So we need to keep those as returning it. And now the LSP is telling us, oops, this one is messed up. And this one is messed up. Okay. Yes, we return void. We have our loop here. This should actually work here. So yeah, we can actually test this out now, and we're gonna have to pass in head into all of these. Whoops, wait, why are you crying? Oh. And so for all the ones that don't actually read anything, we need to return head explicitly. Otherwise, we can just return, right, delete job might modify the list if the head pointer changes, and so we can just return this inline, but for these ones, we just want to return the old head, like, unaffected. So yeah, this function should work. We have our simple parsing, and we should prompt the user to say, like, enter, does he give us instructions for this? Let's see. Enter, enter option. That's kind of bad naming, but who cares? And we'll do a space here. And then after, I'll explain this in a second. Yeah. So basically, I'm intentionally not including the new line here. We could do that, but then basically the user's cursor will move to the next line when it prompts them. I want their cursor to be right here where it looks like they're typing on this line, and then as soon as they hit enter with scanf, then we're actually going to do this. We also need to handle, so if they don't enter an integer and it can't parse this, I can't remember what the return code is for that, but we do need to handle that in case the user enters some garbage. So we'll just add that as a to-do for later. Process choice, we do this, we loop. And then, yeah, if it's 6, we exit. Save data. That's empty, but that's fine. Okay, and we load data at the beginning. I also wonder if we can't find the file, maybe we just create an empty list. Attempt. So actually, we don't want to exit here. Right, so let's actually, so we're going to do, I think I have this in here, clong, assignment 2.c and /a.out. I wonder if this compiles. Okay, enter option. If I do 0, something invalid, yep, it tells me the valid range. That's good. If I do 1 to display jobs, it displays nothing, right, because there's no jobs. So we actually probably want to handle that explicitly. Right, so remember again, if head is null, it means that we have an empty list. And so we want to say no store jobs, right? And then return, otherwise we print the list. And so now, if we do 1, yep, we get no store jobs. I wonder why. Are we doing an extra print line here with the new line? Process choice. Okay, whatever. We don't need to care too much for the formatting. Let me make this a little smaller so I can see the code better. So what's next? Okay, let's test load data. So we're going to touch, what's this file name again? Jobs.data, right? Yep. And I'm just going to enter a bunch of garbage here. But the thing is, this has to be a multiple of 12. Actually, we can, we should handle this also. So basically, this, with integer division, if the number of bytes we have doesn't fit neatly into one of these structs, like basically one of these structs is half full, it means the file is probably corrupted or it's not actually a job data file. And so we want to handle that also. So basically the way we check that is if the size modulus data type isn't 0. So if this will be 0 if we get a valid file and everything lines up. So if it's not 0, that means the file is corrupted. We can just say corrupted. Exit 1. We can test this now actually. So this is how many bytes? 22. Yep, so that this will be invalid. Oop, did I delete it? No. Okay, touch doesn't override it if it's already there. Good. Yep. Oh, that's interesting. Did I do the parameters wrong? Yeah, that's 12. That makes sense. Bytes read. Size. Got file size %d. That's weird. And we're reading binary. It shouldn't do any buffering for us. Okay, this is interesting, guys. I don't know what's going on. So we allocated with the right size. this is definitely the right size. We call f read with size times 1, which should give us the whole buffer. Oh, maybe this just returns 1 if it succeeds. Underscore throw. Wait, you can throw exceptions in C? That's terrible. Let me look up the docs for this, actually. I do not remember at all. Oh, it's the number of elements. Okay, nice. Yeah, so actually we want to do this. This is actually not bytes read. This is elements read. And so that actually means we want to do this check above so that we know the number of elements to expect from the file size. And then so this is actually going to become if elements read doesn't equal elements. No, we should do this properly. So instead of doing size, we calculate the elements. We f read, instead of 1, this is going to be elements, and the size of each element is size of this. Let me make sure that's the right order. Size n, yep, so this is our size, this is n for the number. And if we can't actually read that many elements, we can just cheese out and say say it's corrupted again, because we don't, like, if we're already failing, there's no need to have a nice error message. Right, so this should do that now. Input file corrupted, and it fails. Okay, good. So we don't need this size business anymore. Yep, it's corrupted, but I bet you if we go in here, and right now if you look here, it's 22 bytes in VIM. If we make it, if we look at jobs.data, oh, why is it? I guess there's a new line or something we're missing. Okay, now it's 24, so this should actually work. 1 for print. Yeah, and so this is actually our ASCII being reinterpreted as an integer. So you can see we're actually getting valid data here. In real life, no one should be editing this with a text editor because it's just literally these binary integers. And because we do all the manipulation ourselves, if no one messes with the file, we save it on exit and then load it back up again. So the data should remain the same, even though this looks kind of sketchy that it's just sort of random garbage. But yeah, okay, that's our load data function working. And actually, we can do save data now. That shouldn't be too bad. And this needs to return void. So yeah, this is almost going to be the same thing in reverse. And we can even copy some of this code already. Except this is going to be write binary. It's null, and we're going to say open for writing, and not creating empty list. And we can just have an early return here. We don't need to return anything, so whoops. This is funny, I'm getting some Rust suggestions in here. Okay. And now we kind of want to build our buffer again, right? So we need to calculate how long this linked list is. And the only way to do that is just by looping through the whole thing and just checking everything. So we need a temporary variable so we don't throw the head here, because we're going to be like overriding this. So make another node type, temp equals head. So while temp doesn't equals null, temps equals temp, arrow next. And then every time we do that, that's another element, so we want to increment this guy. And so now we know how many elements there are, we can figure out how many bytes to allocate. That's going to be elements times size of data type this time, right? Because we're not saving the pointers, we're only saving the raw ints. Struct, this is 12, okay, that's the number of bytes. Now we can allocate the buffer again, and we can just cheese the error handling, right? Buff, we have our, we call it, actually I'll call it size again, right? We don't have to refactor this code. Okay, and then we malloc it, we check that. And then now we need to do the opposite. We need to copy into the buff. Actually, we don't need to allocate memory. We can just do this inline. What am I doing? And we don't even need to know the number of elements. We can just f-write this and have the C buffering take care of everything. This gets even easier now, right? So now this just becomes, we're just going to loop through each thing. Head. And so the pointer we want to write is just head arrow data. I think it's node, what do we call it? No, it's data type, dude, these names are killing me. 1 record to file, please. And this needs to be a pointer to the data. This is our data type, yep, so we're gonna write out all that data. So let's look at this. So we write out each thing. And actually, I forgot to close this in reading. That's important. We don't want to run out of file descriptors. Yep, so we mem copy that in. Yep, okay, this is good. We do save data. And I think we're already calling this when we do 6. Yep. And we can just do a printout at the bottom, right? Because in save data, we're about to exit the program. So it's good to let the user know, hey, your save actually worked and your data is saved at this place, right? So printf. Now we're going to say job to, we're going to give them the path they entered just so it's obvious. To, dude, why is spelling so hard? Path. What? Oh shoot, I'm putting this in the wrong place. So we want to close it and then say hey, and I think this might be, this can probably fail, but who cares if it fails, we don't really care. Okay. Ooh, that's interesting. So if we close the stream, then fread probably fails. So we should handle this case so that we don't loop forever. Fread, nope, it's not fread. We want, nope, not this either. Scanf, that's what I meant to say, not fread. And what's the return value? Okay, so it looks like it matches the number of things it parsed, right? So in here when we're reading, this is going to be I wonder if this also happens on failure to parse. System error, get the hell out of here. This might also just be, okay, so it looks like that works. And here we'll just continue to do another thing. And we'll say, yeah, we'll just say choice must be in the range, right? So I do this. Oh. Wait, why does that not work? What? This should call scanf again, right? This is puzzling. Oh, because it's, maybe it parses one thing? I'm really missing the debug macro from Rust right now. %d result. Okay, maybe it's just spamming 0. Okay, we'll exit the program if it's invalid. Like, they shouldn't be doing that. Yep, okay. And we can delete this debugging. And here we go, okay. Yeah. Oh, okay, we probably want to check EOF too. I have no idea what header file that's in. Right, we want to do that, and so we use Control D, yep. End of user input stream. And actually we want to do the printf here after the scanf so that it looks pretty, right? So we do this, it prints the error here, or if we close it, it prints this after. Yep, so that looks good. Our reading, I think, is good. Let me think. Okay, we're gonna save right away. Okay, we can't really test this until after. right? Because the only way to test this, because we're reading in the same data we're writing out, would be to read in like an empty thing, add some stuff, and then write it out, and then check it actually was modified. Here, the best we can do... Oh, actually, no, we can remove this better, right? So now we should have the list in memory, and if I do save and cat this out again, it comes back, right? Because we deleted it in this terminal, so the file is gone, and so this is actually saving correctly. That's good to know. Okay, so that's the I/O part done. Now we need to just handle these other functions here. Save data. So search jobs. This can be pretty easy. This is kind of like print, except we'll do some kind of similar handling here. Except we only want to print when we find it. Job number equals... Okay, now we want to get input for the desired thing. Where's my scanf? We can just copy this code. This error handling is very annoying. You know, it'd be nice to make, if we're gonna fail the program here, yeah, let's just make a function called like, and this is literally just gonna be all of this business worked into one thing, except this is going to be exit and this isn't necessarily choice, it's value, because it could be anything, and then we want to return this at the end. This is going to be what? Oh, dude, my VIM is freezing. Are you kidding me? Okay, at least I could queue it up. And we're literally just going to print out parse error message, and yeah, so actually here this simplifies everything a lot. So all we have to do is enter option, and we can put choice here, get user input, and this is going to be the same, right? Now we don't have to do this annoying stuff. We can just say, okay, check the head. This is going to be like desired num. Okay, and so if the job number equals desired job num, then we want to print all this stuff. And actually, because we're not doing this, let's not indent. And then when we find it, we want to return data.job number. Found in job, right? We do our new line, so it's nice. We do need to increment I and do this, and then if we get here, it means we went through the whole list without this if running and exhausted the whole loop, which means that we couldn't find it. And so we're just going to say like to find job found in job and that's the index. Okay, able to find job number, and this is just going to be desired job num. Okay. All right, so what is it to search again? 1 is display jobs. Oh, 2 to search jobs. We need a print to prompt the user, but if I just put in like 10, unable to find it, yeah, because it's looking for this weird stuff. Actually, this should work if I do this. Oh, so 2, this, nice, and it found it, okay. And actually, so we're gonna move these extra print lines. We want it in the loop to spread these out. But actually, after every query we execute, process choice, we also want to do a new line, just so we don't have this problem. And then we need to prompt the user also to say, and then we'll do the same thing above where we do we basically prompt them without this, and then we do the new line after, so it looks a little nicer. And so this is going to be enter job number to search for, right? So if I do 2, if I search for 0, it's not going to be found, right? But if I do search, and I want to search for like this guy, job number 2, from our random data, we get that. I wonder why though, enter option, it looks like this, it's not, why is this printf not running? Because before enter option it should, oh, we must be missing a new line somewhere else. Display. Oh, yeah, duh, we're missing, these all need to be new line. And same thing here, I just copied this code before doing the new line stuff. So that explains it. So we do this, search for something random, doesn't find it. If I do search for something, then yeah, this fails. Or if I do search and I close it, yep, end of input stream, that works as well. Okay, so that's handy to have this function. We're basically avoiding having to duplicate a bunch of code here. Okay, yeah, so we're making good progress. Search jobs, let's actually do all the read-only ones first because that's a little easier. We'll save the best for last. And so this is basically going to be search jobs, except we don't have to print anything. We're going to say total job, what do they call job size? 0, right? So an average is we just sum up everything and then divide it by the number of things. So actually we do need an I to just count how many things we have. We don't need any of this branching. We want to go to the next node, increment I, and then total job size plus equals head data job size. And this needs to be 0. This is 0. And we're just going to do printf %f average. So we're going to have to cast these to floats, right, so that we do the correct division. Whoops. Divided by float, the count, right? And this is going to be avg with a new line, of course. And so if I run this right now, we should get a massive thing for, what is this, 5 is total job size, right? Yeah, okay, that seems reasonable. Because I just typed in some random data. Okay, so now on to the fun part, add and delete. This is actually when we get into like prime linked list time. So we need to search for it first. And so maybe, how do we want to do this? Let's go back to the assignment. He might want us to use the same function here. Okay, maybe he doesn't. I can just, no, actually we'll just implement it manually, it's fine. So basically add job. We add a job to the end of the list. But I think he said something about job number is unique, and so we don't add it if it's already there. He said it's like a database, right, where kind of the primary key is like the number. Number. Okay. I guess actually not. This is fine. I guess we add it to the end no matter what. And so add job, we need to create a new node here. Equals, we can just copy this code because we have the error handling from malloking stuff. New Yeah, so we try to malloc that. Oh man, I hate this formatting without the space before malloc, but it's going to fight me on that. Okay. And we're always going to return head, right? There's the special case where I'm sure there's a nice recursive way we can do this, but we're just going to brute force it. So if head equals null, then we want to assign it here. Otherwise, if it's not null, then it means we have a list we have to handle, right? So while so we want to loop through the whole thing and say, no, actually we need a temp here. Let's copy this. Because we can't reassign our head because we need to return it at the end. Let's see. Okay, so we assign our temp. Our temp isn't null. We go to the next every time, except if. So basically, this is we're finding the end of the list. If the next one is null, then we want to assign next equals new. Okay, now we just need to input the data for this actual node and then assign it to the thing. So we need to read in, what is it, 3 pieces of data. So we can just copy the declaration here again. Add node, it's going to be equals get, what did I call it? Yeah, get user input. And we can, well, actually, let's clean this up a little bit. Whoops. So I'm going to make this function actually take in 2 strings. The first one is going to be the prompt, hopefully without a new line, so it looks nice. And we're just going to print out that string. Right, and notice how I'm not doing this. Because actually it should warn us. Yeah, it's potentially insecure, right? Because someone could put in a %s into the prompt and then start reading garbage from memory and maybe leak our secrets. There's some exploits where you can actually get write permission by overwriting return pointers and things like that. So we don't want to get DOS, so we're not going to do that. We print the new line after, we print the prompt before. Now we just need to fix up the places where this is called by basically putting this string here. Whoops, that's not a string. What are you crying about, const? Parse error message. Oh, it was because I was in the middle of this. Yep. So this is going to be enter job number. And then these are going to be basically the same, but for the different things. Enter job type and size. Okay, now that we have that, we can say new data dot job number equals job number. Job size equals job size. Okay, so we create the list. It's not there. If it's not, we loop until we find the end and then link it, and we return the new head. So this should actually work now. All right. It's a little gross. It's one file. It's getting kind of nasty. All right. So let's recompile here. And so we have the list in here already. Actually, let's delete jobs so it's empty. Right. Yep. Creating empty list. Good. So it's empty. What is it? Add job is 3. Enter job number 1. Job type is 2 and size is 4. Okay, so now it should be here. And actually, let's clean this up. Enter option. We want to do a colon here every time. So it looks good. So now actually, if we do display jobs, yep, we see 1, 2, 4. That's what we expect. If we do get average jobs, we get average 4, right? Because 4 is the only one. Actually, we need to handle if it's 0. Get average job size. So if I Actually, we can just steal this handling here. If the head is null, we just print no stored jobs, right? Because there's no average to get, because we'll divide by 0 here if that's the case. So that's good. We fixed that. What else can we test? Let's test. Actually, let's add another one and do this like 8, 16, 32. And then we'll do 6 to save this. Oh no, is that a loop? I don't think we assigned. Hold on, I messed something up here. Temp isn't null. Head equals new. This. This is uninitialized memory. Yep. So we need to say new. We could use calc, and that would fix it too. But this is probably a little easier. We also need to do this when we load. So where we assign data. So we copy into data. We want to assign next to be null, right? And so this should actually fix this. Creating empty list, yep, because we lost it. What is the option again? I think it's what, 3 is create, add job. 1, 2, 4. Display jobs. New job. This is going to be 8, 16, 32. Oh, okay, that's still broken. So it looks like add job. Something with this code. Temp equals head while temp isn't null. Temp equals temp.next. So this is never going to return. So basically when we find the last one, we actually want to break here because we successfully added it to the list by doing this line, and so we're done at that point. All right, so one more time. 3 to create, 1, 2, 4, 3 to create, 8, 16, 32. If I do 1 to print again, right, we get both of those. If I do, 5 for average size, we get 18, which, yeah, that seems like the average of these two. Yep, that's correct. And now I can do, let's do search jobs for job number 1. We find that. If we do search jobs for job number 8, we find it. If we do search jobs for job number 3, we don't find it. And if we use 6 to save, if we do cat jobs.data, ooh, that doesn't look right. Oh, that's funny. I guess it's binary, so cat doesn't like it. But yeah, you can actually see our data here, right? Job number, we did 1, 2, 4, 8, 16 in hex, right? 32. And you can see it's a little wacky. It's in, it should be, what? Oh, so it's in Little Indian, except hexdump is doing something weird and swapping these for us for some reason. That's annoying. But yeah, this is correct, and I bet you if we rerun this guy and print it, yep, we get the same data, right? So that works. Now we just need to do deleting. And delete job. It can be deleted from anywhere on the list, and it looks like we've taken the job thing again. So we'll copy this. Delete job. We can't delete it if there's nothing. Actually, we'll just search for it, not find it, so that's okay. We'll do kind of a similar thing with our little temp here. Get user input. Job. Enter a job number to delete. Same integer warning. Well, temp doesn't equal null. Actually, it's going to look very similar, because we're going to have to link it to the next one. The only thing that's changing head is kind of a special case, but we'll handle the general case first. So yeah, we got our temp is set to the head. If, actually before we do this, oh, this isn't bad at all. So after, so it's not null. So if temp data job number equals desired job num, then it means we found it, right? And so what does this mean exactly? So if temp and head are the same, and these addresses are guaranteed to be unique because malloc can't assign us the same memory. So if these are the same, we want to basically delete the list, or delete the first element. which we can do by, we're going to free, and we're just going to return temp next, right? And just kind of for safety, we'll say head we'll do this properly. We'll say new head is going to be the next one, right? Just so we save that pointer. We're going to free the current one, return new head, and then we're going to say head next equals null, right? Just so that in case we somehow have a use after free, we break the list here, and so this will exit, and we don't have like a weird half-length Frankenstein's monster. So if it's the same, easy case, delete head. If that's not the case, now it's basically a normal delete, right? Where we're unlinking something from the middle of the list. So we actually need to store a prev here also. Prev equals temp. I wonder here, so actually prev, actually we can make this a little simpler. So if prev equals null, that means we're doing the head. So we can, this is all the same. If it's not null, then we want to set the previous node's next to be the next node's next, so it kind of jumps over us. We're just going to call this next, actually. Yeah, I think this should work actually. So we return the new next if it's the first node. We also need to free temp. If we can't find it, we just return head normally. Free. And where do we quit in here? So actually we need to clean this up also here. While headed doesn't equal null. I have to go soon here actually. I gotta speed run this a little bit. So we get the next one, we free the current one. We'll do the same thing here. Assign it to null. We free that one and then reset head equals next right until we loop through. Deleted element. Down here, we'll add a new line because we might delete multiple things, right? I'm going to create from scratch. What is it to create? I wish we could just type in it like a command. That'd be way easier. So add job is 3. So 3, 1, 1, 1, 3, 2, 2, 2, 3, 3, 3, 3, right? And now if we print, we have 1, 1, 1, 2, 2, 3. So if I do 4 for delete, job number 1, deleting first element, if I print now, we only have 2 and 3. Okay, and that was supposed to be freed. Now if I do 4 for delete job and say delete job number 3, deleting non-first element, and this should link. So actually, if you think about the next pointer here in job number 2, it's pointing to null, right? Because it's the last element. And so in job number 1, originally this next pointer points to job number 2, but we're actually going to make it jump over. And because this is null, this logic should actually work when we print this here. Yeah, we just have job number 2. And then this is the same trivial case where if we delete another job, job number 2, now we should have an empty list if we print it. Yep, no stored jobs. Cool. So yeah, I'm going to just read through this. I think this is everything implemented. I'm just going to do a bit more testing, make sure this is all solid. But yeah, this is the end of the speedrun here. We finished the challenge. Hopefully it's a good time, and I'll see you guys in the next one.